So last time we completed the hashing concept of hashing, which covered hash tables and hashing functions, and then I explained to you the concept of collision and the concept of resolving collision using chaining. There is another option through which the collision can be resolved as well, that is called open addressing, and a couple of others as well. But instead of going for the second option to resolve collision, first of all let us focus on the mapping function part of the hash tables or hashing concept this time, and then after that we can cover the second method of collision resolution. Now the keys in the real world are not always in terms of numeric values, right? For example, if you consider the flight number, for example, usually PIA flight numbers are PK, like there is a digit and there are characters involved in that as well, bank account numbers, right? Basically keys represent unique identifiers, and these unique identifiers can be alphanumeric and alphabetic and numeric as well. So these are not always the subset of a set of natural numbers. Characters can occur in keys as well. So but if you see the hash table, which is basically an array whose indices are in integer form, right? So we need to convert the alphanumeric or character keys into this integer form, for which one of the suitable representation is the radix notation, right? So the radix is a notation which can be utilized to convert alphanumeric keys into their numeric equivalents. Okay. Now for example, if you have a key, let's say it's PT, right? This is a key. Now what you can do is you can first of all get the ASCII values of these two characters. For example, P has the ASCII value 112 and T has the ASCII value of 116, right? So then what we can do is that we can convert it into a numeric form. We can convert this PT into numeric form by summing its ASCII values, okay, 116, right? And we will get a new value, for example 228. Now this is a numeric value which represents PT, but this approach is quite naive. Why? Because PT and TP both will have the same numeric representation, right? So when we have same numeric representation for totally different character strings, then the mapping function will produce same slot for both of these. It means that it will result in more collisions, right? So we need to convert the alphanumeric or character type keys into their numeric equivalent using a better option, so which is the radix notation. So in the radix notation, what we do, we multiply the least, okay, we multiply the least significant or maybe the most significant digit as well with a number. For example, if you see here, we are using 128 radix notation, so it's not that complicated. What we do, we multiply the first character with 128 and the rest of the characters are summed as it is. So in this case, the numeric value which we get for PT will be different than the numeric value which we will be getting for TP, right? So this radix 128 notation resolves this issue. but it does not resolve this issue for every type of string. Still there will be certain strings for which same numeric representation can occur. Right. So this visually shows the relationship between hash functions and keys. So these are your keys. This is the hash function. You pass your key to the hash function, and the hash function tells you which slot to use, or it tells you about the key, right? So this hash function is a very important feature in the whole concept of, in the complete concept of hashing. It is quite important. So there are 4 rules which are very critical, rather which dictate or help us to identify a better or a good quality hashing function, right? For example, the first rule is that the hash value is fully determined by the data being hashed, right? For example, let me write a hash function here, right? And in this hash function, as I wrote this thing in the previous lecture as well, for example, the hash function is int hash fun. It receives a key, right? It receives a key, and what it does, it returns 23. That's all. Now if you see here, this hash function is receiving the key, but it is not using it at all, right? So this first rule of a good hashing function is not being followed here, right? So the good hashing function always utilizes the key to find or identify the slot in the hashing table where the key is to be saved. So the first property of a good hashing function is that it will use the key. The second rule or the property of a good hashing function is that it uses all the input data. For example, if your key is equal to pk, right? This is maybe a flight number and this is a key. So your hashing function will, for example, let's suppose if it uses only last 2 characters or digits of this, so it's not going to be a good hashing function. It should use all the values of the key, right? So the first rule is that it should use the key. The second rule is that it should use all the input data, right? And the third function is that the third property is that the hash function uniformly distributes the data across the entire set of possible hash values. So it means that if we have a hash table and this is a hash function, so this hash function will try to use this slot, it will try to use this slot, it will try to use this slot, use this slot, and each and every slot, right? So if a hash function is only using, let's say, first half of the hash table, then it means that it is not uniformly distributing the keys across the hash table. All the keys or majority of the keys are going to the first half of the hash table, so it is going to break the third rule, right? And the fourth rule is quite interesting, that it should generate very different hash values for similar strings, right? For example, cat is a string, act is a string, right? Now if you see, both are different, but the characters used in these are almost the same, rather the same, with an exception of their order. So if we pass these 2 strings to a mapping function, then the mapping function a good mapping function will produce different slot for this and different slot for this, right. So these are the 4 rules of a good hashing function, right. Now, now consider this example as a hashing function. I will give you some time to go through it and see what it does. Now, if you see here, it receives a string. It has a table size as an input. This is basically size of the hash table. Now, what it does, for example, we have a string. Now, what it does, it converts, it gets the ASCII value of the first character, second character, third character, fourth character, and fifth character. It sums it up and divides it by the size of the table, and it returns the slot number of where this key is going to be stored, right. So this for loop sums up the complete string. Basically, since it is summing it up, and it's of type integer, so it will be summing up its ASCII values, right. And then the sum is divided by the size of the table, and the remainder is returned. So you will get a slot in the hash table. Now what we will see that which of these 4 rules does this hashing function violates, and which of these 4 rules does it follow. Now, if you see the first rule says that the hash value is fully determined by the data being hashed. It means that the first rule is being followed, because it was the hashing function which I just showed you was utilizing the data. Secondly, it was utilizing the complete data as well. So the second rule is being followed as well. So these 2 rules are followed. Now, if we see the third rule says the hash value uniformly distributes the data across the entire set of possible hash values, right. So this on the face of it, when you see this function, it is quite challenging to say that it uniformly distributes the keys across the entire set of hash values, but actually it breaks this rule, because for looking at it, it is not obvious that it does not uniformly distribute things. But if you were to analyze this function for large input size, you will see certain statistical properties which are bad for hashing, and this thing I will be covering in this maybe this lecture or the next one, the statistical property. So for a hashing function, for example, you have this hash table, this is the hash table, and you have got this mapping function, and so for one key, for example k1, you can, by giving it one key, you cannot determine that it is uniformly hashing or uniformly using all the slots of the hash table. But what you can do is you can write a piece of code that maps, say 1000 keys or maybe 10,000 keys, and then you make an histogram that okay, for to slot number 1, let's say 100 keys were mapped, to slot number 3 200 keys were mapped, and for slot number 3 which is index number 2, let's say 800 keys were mapped. So it obviously shows that this slot is intensely loaded as compared to the rest of the slots. So there you can by this method you can identify if a hash function is uniformly distributing the keys in the table or not. But having said this thing, there are certain statistical properties which you can identify without even programming such stuff, which I will be talking about later. Now the fourth rule, we are talking about this hash function, and we were verifying if this that hashing function follows these 4 rules. So it followed the rule number 1, it was following the rule number 2, it was not following the rule number 3, but you had to code it. But we know from the bookish knowledge that it was not following rule number 3. Now rule number 4. The rule number 4 says that the hash function should generate very different hash values for similar strings, but keeping the example of ACT and CT in view, it is going to produce the same slot, because if you see the hash function, so it is not following the rule number 4, but if you see the hash function, it is simply summing all the characters. It is not using any radix 128 notation or any other such notation. So this hash function is breaking the rule number 4 as well. Now it's quite challenging to make a hash function which follows or satisfies all of these 4 rules, right? So maybe you can write a hash function which satisfies the majority of these rules, right? Because ultimately collision will occur in the hash tables, but we need to minimize it, and to minimize the collision, these are 4 guiding rules which can enable us to write good hash functions, right? Now in order to make or write hashing functions, there are 2 methods. Although you just saw this hash function here, but generally writing, there are 2 methods to write, where was I? Yes, to write a good hash function. These are divisive methods and multiplicative methods. Both have their advantages and disadvantages. Now in the divisive method, what we do is that first of all the key must be transformed into an integer. The value is then telescoped in the range of 0 to m minus 1, where m is the size of the hash table, right? So since the index of the array, depending on the programming language, but keeping ourselves restricted to C, C++, so it starts from 0. So that is why it is telescoped between 0 to m minus 1. Otherwise, if some programming language starts indices from 1, then you may change the range from 1 to m. So usually what we do is that we divide the key with the size of the hash table, and we obtain the remainder. So if we have the key 12 and the hash table has 100 slots, so my mistake. If we have key 100 and the hash table has 12 slots, so we will divide 100 by 12 and the remainder will be 4. It means we have to store this key 100 in slot number 4. So what is the obvious advantage of this hash function? Okay, the obvious advantage of this hash function is that it's very quick. It works in order of 1 time, right? So it's a single statement. So it works in order of 1 time. This is the advantage, right? But there is a catch or disadvantage as well. That is the size of the hash table, right? Now, for example, if you see here, this is a key 8, and using the hash function which I demonstrated to here for a hash table of size 8, right? So if I pass key 8 to the hash function, it will give me slot 0, fine. If I pass 7 to the hash function, it is going to give me slot 7, no problem. I pass 12 to the hash function, it is giving me slot number 4, no problem, so on and so forth. But if you see here a pattern, the binary equivalent of 8 is 1,000,000, binary equivalent of 7 is 111, so on and so forth. This table mentions the binary equivalent. Now if you see that the slot which is assigned to a key is determined by only the lower 3 bits, if you see, lower 3 bits. This one is not being used. if you see here, the lower 3 bit dictates that where this 34 is going to be saved, right. So this is the statistical pattern which I was talking to you about, which tells you that if a hash function is going to uniformly distribute keys into the hashing table or not. Now if you see here, the hash values are being determined based upon the lower 3 bits. Now at maximum these can be 111, which represents 7, right. So it means that the first 6 or 7 slots of the hash table are being intensely used. So and the complete and the complete input which is required to be used by the rule 2 of the good hashing function is not being followed, right. So that is a limitation, and that is not due to the hash function, that is due to the size of the hash table which we have set. So the practitioners recommend that m should not be a power of 2 like 2 raised to power 4, it results in 8, right. So any size of the hash table which is equivalent to the any power of 2 is not a good number. So try to avoid that. Usually you can go for prime numbers which are good to be set for the size of the hash tables, right. So or you can go for go for prime numbers not close to the exact powers 2, or a power of 10 should also be avoided. Now these figures have been obtained based upon various analysis, and I am not going into the details of those analysis here because that is not within the scope of this course, but these things should be kept in mind while fixing the size of the hash table, right. Now this was the divisive method of writing hash functions, right. The next method of writing hash functions is the multiplicative method. Now in the multiplicative method you use a random number a in the range of 0 to 1, right. You generate any random number, for example 0.67, you generate that number. Now what you do is you multiply that random number with the key which you have, and then you take the fractional part of that random number. Don't take the fractional part of that random number, instead take the rational fractional part of the resultant which you obtained by multiplying the random number with the key. Now once you have taken the fractional part, the number from the above step is multiplied by size of the hash table. Now when you multiply this fractional the number from the this step with the size of the hash table, the integer portion of the result is the slot where you are going to store your key, right. So and this integer portion will be in the range of 0 to m minus 1. So it has an advantage that it does not depend any size of it does not depend upon the size of the hash table, right, because in the divisive method the hash table size was important because that resulted in if the hash table size is power of 2, that resulted in breaking the rule number 2 of a good hash function. So advantage of a multiplicative method of writing the hash function is that it is not dependent upon any value of m, right. So this is the numeric example, but this quiz I will be telling you how we will be conducting it, but your reading assignment is if I think I have emailed to you the book, the Corman's book of algorithms. There is a chapter on hashing specifically dedicated to hashing, and you will find the multiplicative method of hashing there. writing hash function. So I will recommend you to please go through that section of the book, and I will discuss how will we conduct the quiz on this and other few topics, but I will be dropping you a separate email on that, right? So this is it, right? Thank you.